All right, Algebra 2, we're going to move on into Chapter 6 right now when we start talking about a new kind of function here called radical functions. And just like everything else in Algebra 2, we're going to be doing the same two things here in Chapter 6 we do everywhere else. We're eventually going to be learning how to graph this new kind of function and how to solve equations with this new type of expression in it. But right now, 6.1 is just getting our feet wet with when we start talking about roots, and you'll notice I didn't put a word in front of that you might have expected. Roots, and then what we call radical expressions. So let's get working into 6.1 right here. The first thing we're going to start talking about are what roots mean, and I'm doing something odd right here, nth roots. So n, of course, can represent any number out there that we're talking about. And so when we talk about roots, the one that everybody's familiar with at this point right here that we're going to start with is square roots. So none of this should be new for you guys. Three quick examples just to illustrate what's happening. The square root of 25, pretty much every Algebra 2 student can tell me that that answer there is going to be 5. And we're not changing that right now. That's absolutely true. But the reason why that's the case, I want to write this down just once right here. The reason that the square root of 25 is 5 is because we were asking ourselves with this question right here, what number multiplied by itself or what number squared is equal to 25? And the answer to that is 5. So the reason here that the square root of 25 is 5 is because 5 squared is equal to 25. So that's an important note right here that we're going to come back to in just a minute right here. Okay, let's go just a little bit further. The square root of 144, again, we're asking ourselves what number squared or what number times itself is 144. That answer there is 12, nothing new. And then just something that was kind of new back in Chapter 4, but hopefully we remember now, when you're asked to take the square root of a negative number, you run into a little bit of a problem. Because what we normally think is that numbers are either positive, negative, or 0. Well, no positive number times itself will equal a negative number. A negative number times itself will also equal a positive number. So that's not it. And 0 times itself is 0. So it's tempting to say there's no number squared times itself that equals a negative number, but what we really should say is there's no real number multiplied by itself that equals a negative. And that opens the door to imaginary numbers. So what we learned in Chapter 4, everybody, is that if you're going to take the square root of a negative number like negative 49, you take the square root of the 49, which is just 7, but you're going to stick an I at the end of that to make that an imaginary number. Okay? All right, so that's just kind of a quick recap of square roots. None of that is really new at all. But now the plot thickens, guys, and we start talking about different roots that are out there, and the first of which we're going to discuss is something called cube roots. All right, so with cube roots now, they have this little extra number that's thrown right there, kind of nestled into this nook within that symbol. And I suppose now's probably a good time that I should talk about some vocab. So anywhere you have room in your notes to cram this down, here you go. That little number that's written right there, the 3, is called the index in a problem like this. Now you'll notice in what we were doing up above with square roots, everybody, there was no number written there. It is implied, it is implied that there's a 2 there for the index in all of those cases, because we were talking about what number squared, what number to the second power would equal 25. So in all of those 3 problems we just did, those were square roots. That's an implied index of 2. Okay, but back to cube roots now. You'll notice we don't write it when the index is 2, but you do need to write it when it's something higher than that, such as a 3. Now, a little bit more vocab I should give you. This symbol right here, everybody, the big root sign right there, is what most people want to tell me is called a square root sign. The problem is, now we're talking about different kinds of roots that aren't squares, like cube roots. So the generic name for that symbol, everybody, is called a radical. And then the number underneath the radical, the number that we are taking the root of, has a name as well, and that is called the radicand. So those are 3 vocab words that you guys should probably know here. Sooner rather than later would be better as we move on into Chapter 6. So Let's answer this question here. What is the cube root of 8? Well, the question now is, what number raised to the third power is going to get us an answer of 8? So now, instead of thinking about perfect squares, like we saw in the previous set of problems, such as 25 and 144 and 49, all of those numbers were perfect squares. Now we have to start talking about a group of numbers called perfect cubes. So we're wondering now, is there a number times itself again that equals 8? So I want to ask you guys just to think about this, and pretty quickly I think you can find the answer. If you started with something nice and simple like 1, well, this goes nowhere. 1 times 1 times 1 is 1, so that's not our answer. If you tried 2, the next integer in line, 2 times 2 is 4, times another 2 is 8. And I guess we just answered the question. The cube root of 8 here is 2. But just like we did before, I want to write down the reason here. And the reason that 2 is the cube root of 8 is because, nope, that's not what I wanted, is because 2 raised to the third power, or 2 cubed, is equal to 8. So that's kind of the explanation here for why the cube root of 8 is 2. How about this second example, the cube root of 125? Well, negative 125. The first thing you might notice, this radicand right here ends in a 5, and that might give you a little bit of a clue what's going on right here, and you might have a guess to the answer already. The cube root of 125, you guys, is going to be 5. We can probably just talk our way through this. 5 times 5 is 25, and 25 multiplied by 5 again is 125. So my answer is definitely going to contain a 5, but that radicand is actually negative. So should the answer be 5i, kind of like this problem right up here at the top of the screen right now, was imaginary? The answer to that is no. The rules are a little bit different for square roots and for cube roots. This answer was imaginary because there's no real number, squared, times itself, that will give you a negative. But think, guys, is there a type of real number that you could cube and end up with a negative? And the answer to that is, yeah, a negative number. The answer here is going to be negative 5. If we multiplied negative 5 times another negative 5, that right there would give us positive 25. And if we multiplied that positive 25 by another negative 5, that gets us the negative 125 that we were looking for in our radicand. So there's something to learn here, guys, from this example right here and this example right here. What should we take from this? Up top, the square root of a negative number has to be imaginary, but the cube root of a negative number is real. It just needs to be negative. And the last problem I had here isn't really one I would expect anybody just to look at and be able to figure that out. But if we were in class right now, I'd say, hey, grab your calculator and play around a little bit. See if you can find a number that's going to be the cube root of 343. What number times itself again is going to equal 343? And the answer to that, hopefully you found it after you thought about it for a minute, the answer to that is going to be 7. Now, two quick things. I want to show you guys some stuff on the calculator right here. Unfortunately, I'm using a different calculator than what you guys have, but they work pretty similar right there. So you might have just grabbed your calculator and played around with a little bit and tried 7 times 7 times 7 and said, woohoo, there's the answer, 343. But I want to remind you guys, your calculator has what's called a caret key. Now, on mine, it looks very different right here. It's this button right there, guys. But you can type it in. For you guys, the caret key, I think, is about halfway up the keypad and off to the right on your TI-84. So that's, of course, going to get you the same answer as 7 times 7 times 7, but it's a little bit faster. The other thing I wish I could point out to you guys, I'll just have to talk you through it, is that on the very left-hand column of keys on your TI-84, I want to say the third or fourth button down from the top is the math menu. And if you guys were to hit that math button on your calculator and then, I believe, type in number 4, that's going to get you a cube root key. So for my calculator, I've got to use this button right here. I've got to type in the 3 for my index, and then you can put in your radicand of 343, and boom, there's our answer of 7 as well. So your calculator will certainly do cube roots for you, just like it'll do square roots. That's just something we need to practice here early on in this chapter. Okay, so that's just kind of a little recap of where we are at the beginning, and here we go. I wanted to throw not square roots, not cube roots, but now some miscellaneous roots at you guys. The first one here, the sixth root. There's no cool name for it. The sixth root of 64. We're looking for a number that can be multiplied by itself over and over and over again, used as a factor 6 times, and get a product there of 64. Well, two things I'd ask you to think about. Number one, would you guess that if this number is going to get multiplied by itself over and over and over again and give us an even result, would you guess that this answer is even or odd? Well, hopefully you've kind of thought about this at some point in your life. Even times even is always going to get you another even number. Odd times odd is always going to get you an odd. So if we're just doing repeated multiplication and getting an even number, our answer should be even. The second thing I wanted you to think about, would you guess this number is going to be big or small if I have to multiply it by itself, using it as a factor 6 times, and end up with an answer like 64? And the answer to that is it's going to be pretty small. Answer to this one, guys, is going to be 2. Let's think about that real quick. This is a tedious way to write it out, but 2 times 2 times 2 times 2 times 2 times 2. Where does that get us? 2 times 2 is 4, times another 2 is 8, 16, 32, and 64. And that's the radicand we were looking for. So even though you guys might look at a problem and say, I don't know what the sixth root of 64 is, I don't expect you to know that already, but it's one that isn't all that difficult to figure out, even without a calculator. You just got to think about it a little bit. Now, the second example I've given you on this page is a totally different thing. The fifth root of negative 100. Well, we kind of learned something from this previous example we did down on the bottom. If I got rid of the last 2 and just did 2 times 2 times 2 times 2 times, there we go, 5 2s, 2 to the fifth right there, guys, is 32. That is smaller than what we needed right here. So maybe the answer is 3. So let's try 3 to the fifth. And again, this gets a little messy to do in your head. So I'll type in 3 to the fifth power, and I got 243. That's not the answer that I was looking for either. But I want you guys to realize this answer right here was smaller than 100. This answer here is bigger than 100. That means the answer is not 2 and it's not 3. It's probably somewhere in between 2 and 3. So I wanted to show you this example just to let you know that not every radical problem out there, not every root problem is going to have a nice clean answer. And once in a while, you kind of have to bite the bullet and just go to your calculator right here and say, okay, gotcha. If I wanted to find the fifth root of a number like negative 100, you are going to, oh, my calculator's fancy than yours. Sorry about that, guys. Let me do this. There you go. That's the answer your TI-84 would have given you. Sometimes you got to bite the bullet and use a decimal answer right there. Although we'll talk about something new in just a moment. Depending on the directions, you'd want to follow that. But usually in Algebra 2, we round to 2 decimal places. So this would be a negative 2.51 if we had to round that. So negative 2.51. And I just wanted to remind you guys, sometimes you're going to end up with irrational answers here. Not imaginary. There's no I here because it was a fifth root, an odd index here of a negative number. So we did end up with a real number, but it's still irrational. All right. So that's just kind of a recap, everybody, for how to do square roots and then teaching you how to do cube roots and some new things onto the big concept right here in section 6.1, simplifying radicals. Now, this example that we're going to do first right here is straight out of chapter 4. Yeah, I believe chapter 4. We talked about how to do this. You also learned how to do it last year in geometry, although in geometry, your calculator would do most of this work for you. But I warned you guys back in chapter 4, just relying on the calculator isn't going to help you because later on in the year, like, right now, we're going to start simplifying radicals that have variables in them. And your TI-30 from last year in geometry isn't going to help you at all with that. So let's talk about the process right here for how to simplify a radical. What we're doing here, guys, is we're trying to take a look at our radicand, which in this case is 75, and we're trying to split it up into the product of two numbers. Now, for example, 75 could be split up as 5 times 15. That's true, but that doesn't help us because what we need here is for one of these two factors to be a perfect square. And I suppose before we go any further right here, you guys want to make sure that you're familiar with this list of numbers right here. Now, we wrote this in our notes a long time ago, but it's probably a good idea for you guys to put this up at the very top of your notes here. Our list of perfect squares is every number that has a whole number for its square roots. So it starts with 0 and 1, but those two really don't help us at all. So yes, those are perfect squares because 0 squared is 0 and 1 squared is 1, but you don't really need to worry about those very much. The more helpful perfect squares are what happens when we take 2 squared, which is 4, 3 squared, which is 9, 4 squared, which is 16, and now I think you see what's going on right here. So I'm going to continue this list for a while right here and hopefully not forget anything. Let's see, 7 squared, 8 squared would be 64. I'll just jump up here to the right. 9 squared is 81, 10 squared is 100, and then of course there's a 121 and a 144. And honestly, that's probably about as far as you guys need to go. All right, there certainly are more perfect squares beyond that. In fact, how many perfect squares are there? The answer to that, hopefully everybody knows this, is infinite. This list goes on forever. Let's see, that was 15 squared. 16 squared is 256. 17 squared, I'm pretty sure, is 289. And it goes on and on and on and forever. Now, as far as what we're going to ask you guys to do with this, if you get to about 144, that's probably more than I would need for you, or enough that you guys would need to have memorized. So, back to the problem at hand, we're looking for a red number over here on the right that divides evenly into 75. And this one's pretty easy to see, guys. 75 is divisible by 25. So I'm going to split the 75 up into 25 times, and 75 divided by 25 is 3. And now, here's the step that I usually skip once we get the hang of this, guys. But there's a property of radicals that says if you have the square root of a product, you can split that up into the product of the two individual square roots. I can make this the square root of 25 over the square root of times the square root of 3. And then you evaluate what you can. Right there, guys, since 25 is a perfect square, we can evaluate that. The square root of 25 is 5, and there's nothing you can do with the root 3, so that just tags along, and that's our answer there. 5 root 3 is our answer for this problem right here. Now, people get confused sometimes, about what it is that we've just accomplished right here. Well, this really is kind of a bygone skill here, guys. It was more important back in the day when math and science and engineering students didn't have calculators that could tell them what the square root of 75 was. So here's kind of what I want you guys to see here. The square root of 75, I think we all know, is going to be an irrational number, a messy decimal, and that's really easy for us to come up with that answer. But back in the day, they didn't know that. But they did know that the square root of 3 was about 1.732. So we just came up with an answer, guys, of 5 times the square root of 3. Now, I want to prove to you here that what we just did not change the value of this number. It just changed the form. So check out what 5 root 3 is as a decimal. Exactly the same as the square root of 75. But back in the 50s, and 60s, maybe even before that, okay, what students had to do is take 5 now and multiply it by a memorized decimal approximation for the square root of 3, which I believe is 1.732. Good high-level math students back in the 50s needed to know this, and they would multiply that out by hand and get an answer of 8.66. Now, is that exactly the same as the answer we just came up with? Not exactly, but it's a pretty darn close approximation. So that's the way we did it, or they did it back then. That's before my time, too. So that's how you simplify a radical. Okay, now most people say, all right, that's not that bad. Then they lose their head a little bit when we get to this next one. Now we've got variables entering into the mix. Things get interesting at this point. So what are we going to do? We're going to try to split up this radicand into the product of a whole bunch of perfect squares. So the first thing we have to do is deal with the 108, which you'll notice is not in my list over here on the right. Now, I taught you guys a method for doing this back in Chapter 4. I want to remind you you of that method right now. There are actually a lot of perfect squares that divide evenly into 108. A lot of people start reading the table here and move down. And if you do that, you're going to find that 4 divides evenly into 108. If you went a little further, you'd also find that 9 divides evenly into 108. But that's the wrong way to approach this, guys. What we really want is the biggest possible perfect square that divides into 108. So here's how you do that. The largest number that divides into any number is that number itself. 108 is the biggest number that goes into 108, but that doesn't help me. So the next thing you would do is take half of that number, 108 divided by 2, and that gets me 54. Now I go back and look at my list of perfect squares. There's no 54 here. The 54 is somewhere in between the 49 and the 64. But that tells me don't bother checking 64 or any number over here that's bigger than the 54, because all of those numbers are going to be too big. What I need to do then is start at the 49 and work my way. I'm working my way down. I would say it's actually up this list. So let's check 49 first, although I don't think that's going to work. 108 divided by 49. No, sorry, that's my calculator's way of giving you a decimal. The next perfect square was 36. 108 divided by 36. Hey, and that one works. So the square root of 108 is a problem I give almost every year in almost every class because it makes you look at the table the right way in order to get it right. So what am I doing now? I'm splitting up that 108 into 36 times 3. Let's keep going now. We now need to take a look at x to the 4th. And the question now is x to the 4th a perfect square? Is there something that can get multiplied by itself to equal x to the 4th? The answer to that is yes, and it's going to be x squared. I'll remind everybody that when you're multiplying two monomials, you add their exponents together. So x to the 4th is already a perfect square. There's no need to do anything with it, although you'll see in just a moment what my plan is. Next question is similar, but this one bothers people a little bit more. Is y to the 10th a perfect square? Is there some monomial multiplied by itself that's going to equal y to the 10th? And remember, guys, we are adding these two exponents right here to get to this power. The answer to that is yes also. Y to the 5th multiplied by itself would get you y to the 10th. So that means that y to the 10th is also a perfect square, and I just write that down again. But now here we go, z to the 7th. Is there anything multiplied by itself that's going to get you z to the 7th? Well, the only thing that would work would be z to the 3.5 power in each spot, but we're not really interested in decimal exponents right now. So the answer to my question here, guys, no, z to the 7th is not a perfect square. Neither was the 108. And look at what we did with it. We found a perfect square that divide evenly into 108, and then we broke it up into 36 times 3. We're going to do the same thing now with z to the 7th. What I hope you guys have learned here is that any even exponent is a perfect square, and any odd exponent won't be. So what do we do now? We need to find something that divides evenly into z to the 7th. All you do here, guys, is you take z and you drop the power by 1. 1 less than 7 is 6, and z to the 6th is a perfect square. Now wait, I'm not done. The z to the 7th gets replaced by z to the 6th times z, and really there's a first power right there. You don't need to write that if you don't want to. So I broke this up. I broke up the z to the 7th into the z to the 6th times z, the same way that I broke up 108 and made it 36 times 3. Okay, we're in really good shape here, guys. Let's talk about where we're going next, though. And I think I'm going to erase all of this junk right here. All right, and let's talk about what we're doing now. What I like to do, this is just my own little method right here, guys, because it's a little faster than breaking up the radical like this. I like to take a look at this expression now, and in the radicand, I like to circle all of my perfect squares. 36 was a perfect square. X to the 4th is, y to the 10th, and z to the 6th. And what we're going to do now, guys, I'm kind of combining two steps from up here above. We're going to take the square roots of all of those perfect squares and bring them out in front of the radical. So here we go. What's the square root of 36? We'll start with a 6. The square root of x to the 4th is x squared. The square root of y to the 10th, you just cut that even exponent in half and we get y to the 5th. And the square root of z to the 6th, again, you take half of that exponent and get z cubed. All of that we were able to bring out in front of the radical. But the radical itself is still there, so there's still a square root sign. And now, what's stuck underneath the radical? Everything that we were not able to circle and bring out its square root there. Okay, so what are we doing now, guys? What's stuck underneath there is a 3 and then a z. You don't need the 1 right there. And guys, that is our simplified answer here for example 2b. All right, so a lot of your homework in 6.1 is going to deal with this concept right here of simplifying radicals. Okay, so that's how you do square roots. Let's keep going here, guys, and let's start talking about cube roots, where we're going next with this one right here, okay? All right, so the first problem we have right here, whoops, sorry about that, is the cube root of 250. Now, you know what, before we go any further, you made a list of perfect squares a few minutes ago. We probably want to put this list at the top of our notes as well. Not perfect squares, but perfect cubes. This is going to be a shorter list, everybody, because these numbers get pretty ridiculous in a hurry. Okay, here we go. Same thought process. 0 cubed is going to be 0. 1 cubed is going to be 1. So those are both perfect cubes, but again, they don't really help us at all. So here's where it starts to get interesting. 2 cubed, 2 times 2 times 2 is 8. 3 cubed, 3 times 3 is 9, times another 3 is 27. 4 cubed is going to be 64. 5 cubed is 125. And beyond that, honestly, that's probably about as far as you guys need, but let's keep going while we're here. 6 cubed is 216. 7 cubed is 343. 8 cubed is going to be 512. 9 cubed is 729. And 10 cubed, I'm hoping you guys could tell me without your calculator, 10 times 10 times 10 is going to be 1,000. Now again, there certainly are more perfect cubes than that. That's just the first 11 of them, but those are probably as many as you guys would realistically need to know for what we're going to do next. So let's dive into example C, the cube root of 250. All right, guys, you'll notice 250 is not in this list of perfect cubes we made, so we're looking for a number in that list in red that divides evenly into 250. And hopefully you guys can see it without too much difficulty. It's going to be 125 right here. So I will make that, however you want to write this here, guys, the cube root of, and I'll split up the 250 into 125 times 2. Now, in the last problem, I told you we're going to circle our perfect squares. Now what we're doing is circling our perfect cubes, which in this case is 125, and we bring out, all right, careful now, not the square root of this number, but the cube root of this number. And the cube root of 125 is 5. So that gets brought all the way out in front, and there's nothing you can do with that 2. It's stuck under the radical here, so 5 times the cube root of 2 is going to be our answer here for C. That's how we've simplified this problem right over here. It's got the same value, but we've written it in such a way that there are no perfect cube factors other than 1, which doesn't really count. There are no perfect cube factors left in your radicand. Okay. Plot thickens a little bit here in D. All right, first of all, you'll notice I gave you a coefficient already out in front. We'll see what to do with that in a minute, but most of our efforts here are going to be focusing on the radicand. So I'm going to leave the -2 there. I'm going to rewrite the cube root, but I think I'm going to need to draw this a lot longer than it was before, and let's start splitting some things up. 135, unfortunately, you guys, is not a perfect cube. So I'll do the same trick I taught you guys with perfect squares. Take 135, divide it by 2, and I think this is going to be a decimal right here. You end up with 67.5. Obviously, that's not in the list either, but that tells me, guys, the 67.5 is right there between 125, and 64, so don't bother checking anything bigger than 67 and a half. We're going to start with 64 and go from there. So let's try it. 135, does it divide by 64 evenly? No, it doesn't. So the next perfect cube in that list, 3 cubed, was going to be 27. So let's check that one. Hey, and that one worked. Okay, gotcha. So we're going to split up this 135 into a 27 times 5. Gotcha. Now, let's move on to variables. Here's the question now. Is x cubed a perfect cube? I think that one is pretty obvious, guys. It's x cubed. Yeah, so that one's going to be a perfect cube. Next question, is y to the 12th a perfect cube? So the question now is there some monomial times itself again that equals y to the 12th? And I'll remind you, whatever these exponents are, we're going to add them together. So is there a number plus itself that equals 12? The answer to that is yes. It would be y to the 4th. So this is interesting, and I want to hit it right here, guys. Y to the 12th is a perfect cube because its exponent, 12, is a multiple of this index right here. The same rationale right here. This 3 divides into this exponent, so x cubed is a perfect cube. This 3 also divides into this exponent, so y to the 12th is a perfect cube as well. That's going to take some practice, guys, but I think you'll get the hang of that eventually. Now, on to the fun part. Is z to the 20th a perfect cube? Answer to that is no, because 3 doesn't go evenly into 20. So what you need to think of is, okay, what is the largest multiple of 3 less than 20? Well, 3 doesn't go into 19 either, but 3 does go into 18. So we're going to make z to the 20th turn into z to the 18th, because that's a perfect cube, times z to the, there were 20 z's, we just used 18 of them, there's 2 of them left over, z squared. And now we're under our radicand, we're talking about cube roots, so we circle all of the perfect cubes. 27, x cubed, y to the 12th, and z to the 18th. We're going to take not the square roots, but the cube roots now of all 4 of those perfect cubes and bring them out in front. So let me get this junk out of the way, and then at that point, okay, here we go. All right, guys, first things first, the cube root of 27 is 3. We're going to take the negative 2 that was already out there to begin with and multiply those things together. So negative 2 times this 3 is going to give us a negative 6 out in front. Let's work on variables now. The cube root of x cubed, what number times itself again is x cubed? That's just going to be x. We did this one already. The cube root of y to the 12th, I just erased it, is going to be y to the 4th. And let me stop right there. Maybe you guys have figured out this shortcut. You're basically just taking, this exponent right here and dividing it by this index. 12 divided by 3 got me 4. It works on the x too. 3 divided by 3 is 1, and sure enough, that's x to the 1st power. We just usually don't bother writing that. Okay, and let's keep going. The cube root of z to the 18th, let's take 18 and divide that by 3. We're going to get z to the 6th power. That's everything that's going to be out in front. Then you're going to rewrite your radical. And guys, people goof this up all the time. Don't forget the index right here. The index needs to get written down there as well. It's still a cube root problem. And what did we not circle? There's a 5 that got stuck there, and there's a z squared at the end that got stuck there. That is all you can do, you guys. So that is our answer here to problem 2D. Again, most of your homework on 6.1 is going to deal with problems like this. Simplifying radicals that might very well be more complicated than square roots and are likely going to contain variables as well. I got one more to do with you guys in this section right over here, just to show you that, hey, as bad as you think things are, they can always get worse. So here you go. Let's do a 5th root, everybody, of 288 x to the 13th times y to the 104th power. Now, in the last couple of problems, we made a list of perfect squares. Then we went back and made a list of perfect cubes. Later on in class, we'll talk about perfect fifths. I guess we kind of need to talk about that now. First question, is 288 itself a perfect fifth? So let me try that, guys. If I hit this button on my calculator, for you guys, it's math, and then I believe you need to hit number 5. And then once you do that, math 5, you have to type in the index now. So you'll put a 5 there, and then I had a 288 on that side right over here. Now, again, what your calculator would give you is this result right here. It's a messy decimal, so no, that doesn't work. So what are we going to try now? Let's take half of 288. So 288 divided by 2 is 144. Let's see if that's a perfect fifth. So the fifth root of 144... Nope, that's not the button I wanted to hit. Sorry. There you go. Your calculator probably tells you this. So 144 isn't a perfect fifth either. So at this point, you might want to start trying to ask yourself, what are some perfect fifths? Well, 1 to the fifth is just 1. That's boring. But 2 to the fifth, we hit this one earlier, is 32. 3 to the fifth power is 243, 4 to the fifth power, now we're getting way too big right away. Fifth powers get big really quick, is 1024. So my question really is, are any of these numbers right here factors of 288? Well, let me remind you guys, 144 is the biggest number that could possibly divide into 288. So I don't need to waste my time trying 1024 or the 243 right here. But what about 32? What if I took, let me get on the right line here, 288 and divided that by 32? Oh, that one worked out. It was 9. So a little bit of investigation right here. You can get to that spot. So all right, guys, we're going to rewrite this now as the fifth root of, and this is going to be a 32 multiplied by 9. And let's see what we've learned here so far, guys. Is x to the 13th a perfect fifth? The answer to that is no, because 13 is not a multiple of 5. So we have to break this up. Go down from 13 until you get to the first number that is a multiple of 5, and that would be 10. So this would be x to the 10th, but that needs to get multiplied by x to the third power to get us back to x to the 13th. Then, next question, is y to the 104th a perfect fifth? No, because 104 isn't divisible by 5. But go down from 104, what's the first number you find that is divisible by 5? That would be 100. So this will be y to the 100th power multiplied by, and then y to the 4th. All right, guys, that's the hard part. Now, I circle my perfect fifths. 32 is a perfect fifth, so is x to the 10th, so is y to the 100th. So one step here and we're done. The fifth root of 32 is 2. The fifth root of x to the 10th, take your exponent, divide it by your index. 10 divided by 5 is 2, so we're going to be able to pull out an x squared here. And then for y, again, take your exponent, divide it by your index. 100 divided by 5 is 20. So that's all you're able to pull out. So we rewrite the radical then. The 5, the little index stays. And what did we not circle? We were not able to do anything with the 9, with the x cubed, and with the y to the 4th. That's as much as you're going to be able to do here, and that's how you would simplify a radical like that. All right, guys, hopefully that gives you some sense of what it is that we're trying to accomplish here in 6.1. I've got more to do here, but I'm going to stop this video and then start another one after that. What we've done right now will probably help you with most of the problems on your 6.1 homework. All right, good luck, everybody.